While researching a purchase of a straight edge for use in woodworking recently, I read a bunch of reviews, and I was struck by how many of the reviews said something to the effect of, well, I don't really know how straight this straight edge is. People don't realize that in principle it's possible to test a straight edge basically to any level of precision you want by comparing the edge to itself. You don't need any other reference straight edge, reference to straightness to really test, especially if you're not talking about extreme precision. So I looked for YouTube videos to see about what people might say about testing straight edges, and I found 3, 2 of which got it wrong. And so I felt there was a need to really teach the method of reversal, which is how we can test a straight edge by comparing it to itself. My point here is to teach the method. I'll teach how to do it correctly, and I will explain in detail why the 2 incorrect methods don't work and the 1 correct method does work. My goal is to make the whole thing clear enough so that you can not only understand but remember how correctly to test a straight edge, and basically how easy it is if you're not asking for extreme precision. So I made some demonstration straight edges that have different errors in them, and you know, the error is quite large, so you probably can see it on just looking at the straight edges. But anyway, the principle of the thing is what matters. And this number 1 is a hollow. It's a bow that's hollow. And number 2 is a ripple. You may or may not be able to see it, but it will become clear. I've marked the top and the left and right edges so that we can always know what the orientation is, and I've marked it on the other side as well. So it says bottom, this is edge number 2, and note that left and left, it always refers to the same edge, and right vice versa. So what do we mean by reversal? Okay, let's look at this edge. What do we mean by reversal? Well, what we mean is we rotate it 180 degrees about an axis. Now in 3-dimensional space, there are 3 mutually perpendicular axes that we could use. So when this, we're on a flat surface here, we can always rotate it about a vertical axis, which is this rotation. Then there are 2 horizontal axes we could rotate it about. One is perpendicular to the edge, that's rotating it this way, and the other is parallel to the edge, that's rotating it this way. So what we do to do the reversal method is to compare the edge to itself, and in order to reproduce itself, what we need to do is draw a line, at least for this moderate precision application. So I'm going to use a pen to draw the line so it stands out really well against this white paper. And so edge number 1, excuse me, I'm going to draw a line. If I'm not too shaky here. From edge to edge. And I'm going to mark it number 1. And then we'll draw a line for edge number 2. Similarly. Now, it's important that the straight edge does not move, so if this were a larger straight edge, I would clamp it or use tape to tape it down or something to make sure it doesn't move, but for this small one, it's not a problem. Now, I'm using, this is not real precise because the errors are large, but if I had a good woodworking edge, I could probably test it without too much trouble to 1/1000th of an inch, 25 microns to you metric folks, by using a piece of MDF and painting it smoothly as a background. But that's a lot of work, and I want to demonstrate the principle. So here's edge number 1 and the line, oops, I forgot to mark number 2. And what's often taught is to rotate the edge about a vertical axis, which is this way. And bring the edge up to the line, and we can easily see, oh yes, there's a bow in this edge, and what we see here is the difference between the edge and the line we drew is twice the error. Great, sounds wonderful. So let's try that with edge number 2. So that we drew this line, we flip this, we bring it up there, and we see, whoops, no error at all indicated. So flipping the edge about the vertical axis is not really the right way to do this. Okay, so let's try edge number 2, and let's try flipping it about this axis, about a horizontal axis this way. And when we do this, we see, oh yeah, look at that. There's our ripple error. Now, if I match up the 2 endpoints, I cover up part of the line. That's just the nature of belly type errors. So it's always legit to move the edge away until you get the the one point of contact, just as long as the distance between these two, between the ends of the line and the ends of the edge are the same. And then once again, we've got shown twice the error along the edge, with this being a reference point, because where do you start? Doesn't matter. All right, let's try that with edge number 1. So we do that, we bring it up, and we see, oh, no error at all. So this flip is sensitive to the opposite sort of errors that the about a vertical axis flip was sensitive to. Neither one really does the job. So let's try flipping about what I call flipping about an axis, a horizontal axis this way, which I call flipping about the line. So we do it this way, and we see the hollow bow in number 1. And if we do the same thing here, we see, oh yes, there's the ripple error in number 2. So flipping about the axis this way, flipping about the horizontal axis parallel to the line, or flipping about the line is what I say, this is the correct way to do it. Now, notice that another way to talk about this flip is that you've got the bottom side up, and right side is right side, left side is left side, that we haven't reversed it left and right. So that's basically it. I hope I've explained the basic method clearly enough that you can understand it and remember it, make use of it. Now I'm going to get a bit geekier and go into a more detailed discussion for those of you who might think that the ripple edge is somehow not representative of real edges, real straight edges, and that you can basically, as a practical matter, get away with doing this. Now, this vertical flip, the flip about a vertical axis, I agree. I mean, I admit that's easier to do than this. There's a lot of practical advantages to it, but it's important. I made a third edge. Well, let me, before I get into the third edge, let me just mention something for you, for those of you that have a mathematical background, and don't panic if you don't have a mathematical background, because you'll be able to understand the point I'm going to make. For those with a math background, we could understand, and it's helpful to think about that this is an even error about the center of the edge. Likewise, this is an odd error about the center of the edge. Now, we've shown that one test is sensitive to even errors and insensitive to odd errors, and vice versa for the other tests that we didn't like. All right, thinking about it mathematically, the thing is that any error can be decomposed into odd and even parts. So one of the poor tests can't see the even parts, and the other one can't see the odd parts. And what we saw for edge number 2, for instance, this being odd, flipping it this way was completely insensitive. You didn't see it. So the result, it appeared that there was less error than is actually on the edge. My point is that when you have a generalized error that has odd and even parts, that it's also possible to get a result such that you will see more error when you do this than is actually on the edge. So now let's bring in edge number 3. So number 3 has a different, let's put it right in the middle here. This has a different error that we're going to investigate. So this is number 3. Now let's flip about the vertical axis and see what we get. And we get something that looks kind of like a conventional bow. Okay, so we think we're fine. We got a conventional bow. It's not too bad, and we're happy. However, what happens when we flip it about the line? Now here we see something different. We see, and I hope you can see this, we see that the error continuously increases in a linear fashion to about here, where we start getting a curvature. Now if we think about it a little bit, that error that increases linearly, that's really, we've got straight lines there, that this edge is actually straight along here, and in fact we can line the straight parts up. And it's straight to about here, and then we start getting a bow. And so we actually have like half this edge is straight, which is an important thing to know. I mean, that's really useful to know, which flipping about the vertical axis didn't tell us. It said it's got a bow up along the whole length, and it's quite significant, whereas here we see the error is actually smaller, and it doesn't exist along half of the edge. And another thing we can say here is that if we consider what we could do to improve this edge along, the whole length of this straight edge, we can see, look, when we line up the straight parts, the edge, if we were to cut this edge down, just file this edge down if it were made of metal, half the difference here, which we can't see because it's covered up, but if we file this, it made the whole edge better than it is now. So two things that we miss by flipping about the vertical axis that we can see by flipping about the line about this edge. Now, some of you are probably thinking, well, that's not realistic. And well, the fact is, understand this. The day that I decided to make this video, that same day I tested the straight edge that I bought as a result of that research I was doing. And I found it has exactly this character, which is basically a little more than half of it is virtually perfectly straight, and then there's a little bow. So this shows the importance of doing this test correctly and the usefulness of it, and hopefully you found this interesting and educational.